Welcome back, DeepVisus Explorers, to Where Vision Meets Depth. Today, we embark on a journey into the foundational ideas of neural network dynamics, inspired by a groundbreaking work that helped shape the field. In this episode, our journey is guided by the work titled Dynamic Recurrent Neural Networks, published by Barak Pearlmutter in 1990. This technical report from Carnegie Mellon University provides a crucial survey of learning algorithms for recurrent neural networks, attempting to unify the various techniques that were emerging at the time. The core question we'll explore today is, how can neural networks be taught to handle the complexities of time and sequence, and what are the fundamental differences in the algorithms that enable this capability? To answer this, we need to first understand what makes recurrent networks special. Unlike traditional feed-forward networks, where information flows in one direction, recurrent neural networks, or RNNs, have connections that loop back on themselves. This feedback loop allows them to process sequences of data, where the network's output at one moment in time is influenced by its state at previous moments. This makes them ideal for tasks involving temporal behavior, like predicting the next word in a sentence or modeling the rhythmic patterns of an insect's central nervous system. The paper categorizes the learning algorithms for these networks into two main groups, fixed-point and non-fixed-point algorithms. Let's start with fixed-point algorithms. A fixed point is a stable state that a network settles into over time. Think of it like a ball rolling down a hilly landscape until it rests at the bottom of a valley. The network's answer to a problem is the state it reaches once it stops changing. The paper discusses techniques like recurrent backpropagation and deterministic Boltzmann machines, which are designed to modify these stable states. Recurrent backpropagation, for instance, extends the well-known backpropagation algorithm to networks with cyclic connections, provided they eventually settle into a stable fixed point. The paper even presents a simulation of a network learning to solve an associative memory task, like reconstructing a rotated binary pattern, by settling to the correct solution. It's fascinating to see how the network, despite having no explicit time-based rules for this task, uses its dynamics to find the right answer. However, not all problems can be solved by simply settling into a stable state. Some tasks require a network to exhibit a specific, detailed temporal behavior, such as following a circular path or a figure-8 trajectory. For these, we need non-fixed-point algorithms. The most prominent of these is backpropagation through time. This is a conceptually elegant, if computationally intensive, approach. It unfolds the recurrent network into a deep feed-forward network, where each layer represents a different point in time. The error is then propagated backward through this unfolded network, from the final time step to the beginning, to calculate the necessary adjustments for the weights. The author shows how this can be applied to continuous time networks and even includes a discussion of learning time constants and time delays, which are crucial for modeling real-world temporal processes. We hear about simulations where a network is trained to trace a perfect circle or a figure-8, showcasing its ability to learn complex, dynamic behaviors that never settle. The script also touches on other interesting non-fixed-point techniques. One is Elman nets, which are a simplified version of backpropagation through time that cuts off the temporal history after a few steps. This makes the learning more efficient but sacrifices the ability to learn from very long-term dependencies. Another is forward propagation, an online learning method that computes the gradient by running a set of auxiliary equations forward in time alongside the main network. This avoids the need to store the network's entire history, making it suitable for continuous, online learning, though it is computationally more expensive. Finally, we have teacher forcing, a technique where the correct output values are jammed into the network during training, a method that can dramatically speed up learning by keeping the network on the right track. So, to return to our central question, how do we teach neural networks to handle the complexities of time and sequence? The paper reveals a rich spectrum of answers. We have fixed-point algorithms for problems that require settling to a stable solution, and non-fixed-point algorithms like backpropagation through time for those that demand specific, dynamic temporal trajectories. These methods offer different trade-offs between computational complexity, stability, and the type of problem they can solve. The paper highlights that recurrent neural networks are not just a big gun to be used as a last resort, but a versatile tool with a variety of specialized learning procedures, each suited for a different kind of temporal challenge. As we close this chapter, remember that the quest for true intelligence, whether biological or artificial, is an unending symphony of discovery. Join us next time on DeepVisus as we tune into another frequency of the brain, mind, and intelligence, unraveling the mysteries that shape our understanding of thought itself.